Hello everyone, today we will discuss about convolutional codes. As we know, in the case of block codes, the encoder takes k-bit message block and produces n-k parity bits to generate a code word of length n bits. That is, code words are produced on a block by block basis. Thus, the encoder for a block code thus required a buffer for storing k message bits. But there are applications in which message bits come in serially rather than in large blocks, in which case the use of buffer may be undesirable. In such situations, the use of convolutional coding may be the preferred method. The encoder for convolutional code acts on the message bits coming serially. It generates the output code word by modulo 2 discrete convolution of its own impulse response with the sequence formed by the present message bit and a few message bits preceding the present one. A convolutional encoder in its simplest form is a finite state machine and consists of a tapped shift register with L+1 stages whose outputs are connected to modulo 2 adders through coefficient multipliers. Since the message bits as well as coefficients G0, G1, etc. GL are all binary numbers, the arrangement is just a binary FIR filter whose finite impulse response is given by the coefficient G0, G1, etc. GL. Here, GA equal to 1 means a direct connection. Similarly, if GA equal to 0 means no connection. No connection or open circuit. The first stage to which the input is given is referred to as the input stage, and the remaining L stages of the shift register defines the state of the encoder. With the contents of the shift register as marked in the figure, the output from the convolutional encoder is given by xi equal to mi into G0 plus mi minus 1 into G1 plus etc. mi minus L into GL. So that is given by mi into G0 plus mi minus 1 G1 plus etc. plus mi minus L GL. So this will be equal to sigma j equal to 0 to L mi minus j into g of j. So this is equation number 1. So you can identify equation 1 as the familiar convolutional sum, similar to the convolutional integral for continuous time signals. That's why these encoders are also called convolutional encoder, and the code word obtained is convolutional code. We can observe that whenever a message bit is shifted into the input stage of the shift register, we will get one output bit, which is given by this particular equation. Right. Thus, for each input message bit, only one output bit is obtained from the encoder. Hence, there is no redundancy introduced, and so no error detection and correction capability exists for the code produced by this simpler encoder. In this encoder, also we can observe that for each message bit shifted into the input stage of the shift register has to go through all the L+1 stages. Thus, each message bit influences L+1 successive encoded bits coming out from the encoder. Now consider a practical form of convolutional encoder with 3 shift register stages. As pointed out earlier, for the generator code to have error correction capability, it is necessary that each input bit should give rise to more than one bit of encoded output bit. This is achieved by using 2 or more modulo 2 summers and interleaving the output bit from them using a commutator switch. In this diagram, we can see that we have used 2 modulo 2 summers and 1 interleaver. The code produced by a practical convolutional encoder is generally referred to as NKL code, where N is the number of encoded output bits produced for one message bit. K is the number of message bit entering the encoder at a time. In the given convolution encoder, there are 3 shift register stages. That is L plus 1 equal to 3. So L equal to 2. This plus 1 indicates the presence of input stage. For the given convolution encoder, we can see that what is N? N is the number of encoded output bits produced for one message bit. So we can see that for one message input, there are 2 output bits are produced at the output. Right. So that is N equal to 2. K is the number of message bits entering the encoder at a time. So at a time we can see that only one message bit is entering the encoder. So K equal to 1. Now since there are 3 shift register stages, for the given convolution encoder, L equal to 2 because L plus 1 is 3, so L equal to 2. So the given convolution encoder is 2, 1, 2 convolution encoder. The output of the convolution encoder is say X. So we can see that X equal to X1 of 1, X1 of 1, X1 of 2. Then X2 of 1, X2 of 2. Then X3 of 1, X3 of 2. Like this. So this is X1 of 1, X1 of 2. Then X2 of 1, X2 of 2, etc. Now we will find the output of the convolution encoder using time domain approach. Consider a convolution encoder as shown in figure. Determine the output sequence xi of 1 and xi of 2 and hence the encoder output sequence x of the encoder shown. Given that the message sequence is 10 1001. So first of all, for the given convolution encoder, the generating sequence, we will find the generating sequence. Generating sequence for this particular convolution encoder. So as we know, this is G0, G1 and G2. And this will be again, so this will be G0 of 1, G1 of 1, G2 of 1. So this will be G0 of 2 and we can see that G1 of 2 is 0 because this is open and this will be G2 of 2. So G0 of 1, G1 of 1, G2 of 1 can be written as 1, 1, 1. So this is the generating sequence for the first stage. And next is G0 of 2, then G1 of 2, G2 of 2 equal to 1, 0, 1. So here we can see that this connection is open. So G1 of 2 is 0. So the generating sequence corresponding to the second stage is 1, 0, 1. Given that the given message sequence is 10 1001. So I am using the notation like this. M0 as 1 0 1 0 0 1. Now what will be xi of 1? Xi of 1 is sigma j equal to 0 to L mi minus j g of j. Right. So here we can see that this will be equal to, we know that L is 2 for the given convolution encoder. So for the given convolution encoder is represented as 2, 1, 2 convolution encoders. This is N, K, L. So L here L is 2. So this can be written as sigma j equal to 0 to 2 m I minus j g of j. Right. First of all, so this I indicates the time index. Time index. So first of all, we will find at time I equal to 0. So this will be x0 of 1. What will be x0 of 1? x0 of 1 is sigma j equal to 0 to 2, I is 0, right? So this will be written as, so m 0 minus j, g of j. So we can see that equal to m0 minus 0, g of 0 plus m0 minus 1, g of 1 plus m0 minus 2, g of 2, right? So we can see that m minus 1 is not there. So the sequence starts from m of 0 only, right? So this will be, this quantity is not there and this quantity is also not there. So this will be equal to m0, g0, which will be equal to, what is m0? m0 is 1 and g0 of 1 is 1. So 1. 1 into 1 equal to 1. Similarly, you can find x1 of 1. Summation j equal to 0 to 2 m1 minus j, g of j. So this will be equal to m1 minus 0, g of 0 plus m1 minus 1, g of 1 plus m1 minus 2, g of 2, g2. So this will be equal to m1 g0 plus m0 g1 and m minus 1 g2. M minus 1 is not there. So this quantity is 0. So you will get it as m1 is 0. 0 into g0 is 1 plus m0 is 1 into g1 is 1. So this will be equal to 0 plus 1 equal to 1. Now similarly, x2 of 1 is m2 g0 plus m1 g1 plus m0 g2. So this will be equal to 1 plus 0 plus 1, which is equal to 0. 1 plus 1 is 0, right? Modulo 2 addition 1 plus 1 is 0. Now x3 of 1 is m3 g0 plus m2 g1 plus m1 g2. So this will be equal to 0 plus 1 plus 0, which is equal to 1. And x4 of 1 is m4 g0 plus m3 g1 plus m2 g2. So this will be equal to 0 plus 0 plus 1, which is equal to 1. Now x5 of 1 is m5 g0 plus m4 g1 plus m3 g2. So this will be equal to 1 plus 0 plus 0, which is equal to 1. And x6 is m5 g1 plus m4 g2 only. So which is equal to 1 plus 0 equal to 1. And x7 of 1 is m5 g2 only. So this will be equal to 1. So xi of 1 can be written as 1, 1, 0, 1, 1, 1, 1, 1. Similarly, you can find xi of 2 and you will get it as 1, 0, 0, 0, 1, 1, 0, 1. So you can do it as a homework. Now the encoded output sequence. Encoded output sequence can be written as x equal to 1, 1, 1, 0, 0, 0, 1, 0, like this. So first the commutator switch will goes to the upper stage, then lower stage, then upper stage, lower stage, like that. So you will get it as 1, 1, 1, 0, 0, 0, 1, 0, 1, 1, 1, 1, 1, 0, 1, 1. Now I will show a shortcut method for finding the convolutional sum. Okay, suppose we have G0 of 2, G1 of 2, G2 of 2 is 101, right? And message sequence is 101001. Okay, so what you can do is you write the message sequence here 101001 and the generating sequence here 101. Now multiply this one with this message sequence, or we can say that if 1 comes, you repeat the sequence here 101001. If 0 comes, fill it with zeros 0000000. Again 1 comes, you repeat the sequence 101001. Now group in a diagonal manner like this. Now add. This is 1, 0 plus 0, 0, 1 plus 0 plus 1, 0, 0, 1 plus 0 plus 0, 1, 0 plus 0 plus 1, 1, 0, 1. So this is the sequence you obtained here, right? Xi of 2 is this. So we found this Xi of 2. Similarly, you can find Xi of 1. How will you find Xi of 1? So write the message sequence here 101001 and the generating sequence is 111. So when 1 comes, you repeat the sequence here 101001 101001 101001. Now group it diagonally. Okay. Now 1 plus 0, 1, 1 plus 0 plus 1, 0, 0 plus 1, 0, 0 plus 1 plus 0, that is 1, 1 plus 0 plus 0, 1, 0 plus 0 plus 1, 1, 0 plus 1, 1, 1. This is Xi of 1. So this is exactly what you obtained here. 110, 111, 11. So here also you get 110, 111, 11. Thank you.